Hey there, kiddos. Okay, so we're going to start with number 34 because that's where we left off. So 34 asks us to solve this equation using the quadratic formula. So my equation is 7r squared minus 7r minus 5 equals 0. To use the quadratic formula, we have to identify what our a, b, and c terms are. So a here is going to be 7, b is negative 7, and c is negative 5. I go ahead and I plug those into my quadratic formula. When I do, I get the negative of negative 7 plus or minus the square root of negative 7 squared minus 4 times a times c, and then all over 2 times a. From here, we go ahead and simplify. The negative of negative 7 is positive 7 plus or minus the square root of negative 7 squared is 49. And then I do 4 times 7 times negative 5. And I get 140, but it's minus a negative 140, which means that it's plus. And then all over 14. Simplify this farther, and I get 7 plus or minus the square root of 89, or 189, sorry. All over 14. So from here, remember, we do not want decimals, so everything I have to do has to be in simplified radical form. I know 189 is not a perfect square, so I'm going to go ahead and do a factor tree over here. So in my factor tree, I'm going to be breaking this down as far as I possibly can. So the first thing that I notice that goes into 189 is 9 and 21. Neither of those are prime, but 9 is a perfect square, so I could stop there. 21 then breaks down into 3 and 7. Both of those are prime, so I'm finished. I go ahead and write out what my factors are then. So I have 3 times 7 times 9. None of those are identical, so I don't have to worry about putting anything together. So I just go ahead and square root each of those. Square root of 3 is just the square root of 3. Square root of 7 is just the square root of 7. And the square root of 9 is positive 3. If we have more than one radical, I multiply the numbers under the radicals together, and I write them as 1. So 3 times 7 is 21. So I get 3 times the square root of 21 is the square root of 189 reduced. So now what I have is 7 plus or minus 3 times the square root of 21, all over 14. The last thing I can possibly do is ask myself, okay, is there a perfect square I can take out of 7, 3, and 14? The answer is no, so this is my final answer. For number 35, it wants us to find the value that completes the square. So it gives me x squared plus 6x plus, and then it gives me a blank. Remember, when we're completing the square, I want to create a quadratic that's going to factor beautifully into the same thing twice. So when we do that, we go to this middle term, we divide it in half, and then whatever answer we get, we square. Okay? So I do 6 divided by 2 is 3. 3 squared is 9. So I need to put a 9 there. I know this works because when I go to factor this, I'm going to get x plus 3 times x plus 3, which I can rewrite then as x plus 3 squared. Okay, so that's how I verified that it works. This leads us directly into 36, which is where I'm actually solving a quadratic by completing the square. So for 36, I have the equation x squared plus 16x plus 58 equals 3. In order to complete the square, I need to get everything that's not an x over to the right-hand side. So I subtract the 58. When I subtract the 8, I get a negative 55. I'm going to leave a little bit of a blank or a big open spot between my 16x and the equal sign, because this is where I'm going to actually complete the square. So in order to complete the square, I'm going to be solving for that beautiful C value, just like we found in the previous problem. To find that C value, I go to the value in front of it, which is 16. I divide that in half. And then I take that answer and I square it. So then 16 divided by 2 is 8. 8 squared is 64. So my C value that I need to put in there is 64. What I do to one side of the equation, I also have to do to the other. So now I have to take the negative 55 and add 64 to it on the right-hand side. On the left, I have a beautiful quadratic that I know is going to reduce. And when I factor it, I'm going to get x plus 8 times x plus 8, which I will rewrite as x plus 8 squared. And then equals negative 55 plus 64 is a positive 9. Now my goal is to go from this step and solve for x. So the first thing I need to do to get x by itself is to square root both sides of my equation. When I do, the square and the square root cancel, leaving just an x plus 8 equals the square root of 9 is positive and negative 3. If it hadn't come out even, I would have had to do a simplified radical form. And then the last step is to subtract the 8 over so that I have x isolated by itself. Then, of course, I have negative 8 plus 3 and negative 8 minus 3. I split it up into two problems. Negative 8 minus 3 is negative 11. Negative 8 plus 3 is negative 5. So my two solutions are negative 11 and negative 5. So the next one up is 37. So this one is just a graphing one. The equation I have is y equals 2x squared plus 8x plus 10. In order to graph this, I have to find my axis of symmetry first. To find the axis of symmetry, I use the equation x equals negative b over 2a, using the same a and b that I had in the previous problem. So a is the number in front of x squared, b is the number in front of x, c is the constant on the end. So when I do that, I get negative 8 over 2 times 2. That becomes negative 8 over 4, which is just negative 2. So what I do is I go to my graph. I go to where x is equal to negative 2, and I put a dotted line. I always want to see that dotted line when we're talking about an axis of symmetry. Now that I found the axis of symmetry, I need to find my vertex. The good news is I've already found half of it. This axis of symmetry value is also the x-coordinate of my vertex. So to find the y-coordinate, I'm going to take that negative 2, and I'm going to plug it back in for the x's in my original equation. When I do, I get y equals 2 times negative 2 squared plus 8 times a negative 2 plus 10. Negative 2 squared is 4. 4 times 2 is 8. Negative 2 times 8 is negative 16. Then plus 10. 8 minus 16 is negative 8. Plus 10 is positive 2. So then my vertex is at negative 2, 2. So that's the first point that I'm going to put down on my graph. In order to graph a quadratic, we need 5 points in total. I have 1. Now I need to find the other 4. The really cool thing about a quadratic equation or a quadratic graph is that it is symmetric across this axis of symmetry. So essentially, if I were to fold the graph in half, right along that dotted line, my left and my right side would match perfectly, which means that instead of having to find 4 different points, I can find 2 on one side and then find their matches on the other without doing any math. So let's go ahead and do this. I always like to pick x values that are extremely close to my axis of symmetry, kind of to ensure that they're going to fit. So I'm going to go ahead and do negative 1 and 0 because those seem to be the easiest to plug in for me. And I'm going to do just like I did with the negative 2. I'm going to plug them in for x and I'm going to solve. So now I plug -1 in here. I get -1 squared is 1 times 2 is 2. -1 times 8 is a -8, and then plus 10. I simplify that out. I get 2 minus 8 is -6, plus 10 is +4. So -1, 4 is going to be one of the points that I put. And then I find its match on the other side of my line of symmetry. I do the same thing with 0. 2 times 0 is 0. 8 times 0 is 0. 0 plus 10 is 10. So that's the next point I'm going to find. And then I find its match on the other side of my line of symmetry. Once I have 5 points, I go ahead and I draw my quadratic as best as I possibly can. A couple fun things to point out is that the direction that my parabola opens directly impacts whether I have a minimum or a maximum value as my vertex. So in this parabola, my parabola opened up. I knew it would because the number in front of my x squared was positive. So if that leading coefficient is positive, my parabola is going to open up like a cup. If that leading coefficient is negative, my parabola is going to open down like a frown. If the parabola opens up, the vertex is the bottom point, which makes it a minimum. If my parabola were to open down, my vertex would be the highest point, which would make it a maximum. Okay, so that's just helpful information. That kind of leads us directly into number 38, which is kind of pulling information from the graph. We're just going to talk through it because I'm not going to draw that for you. So the first thing is, what is the vertex of the following function? Well, I just need to find the minimum or the maximum, which is either the highest or the lowest point. The parabola in 38 opens down, so my vertex is the maximum. I see that that's at the point 3, 4, so that's my vertex. We already identified it's a maximum. The equation in standard form, I actually start with the equation in vertex form first, because that's the information that I have in front of me. So vertex form is y minus k equals a times x minus h squared, where my vertex 3, 4 are my h and k values. So I go ahead and I plug those in, which gives me y minus 4 equals a times x minus 3 squared. In order to expand this out, I need to find my a value. On the graph, this is the vertical distance from my vertex to the next x value. Okay, so to where my next x value touches the graph. So on our example, oh my goodness, my vertex is at 3, 4. The next point down on the graph would be 2, 3. So the vertical distance between y equals 4 and y equals 3 is -1. So that's what my a value is. Once I identify that a value, I just go ahead and I'm going to FOIL out the x minus 3. I'm going to distribute the -1, and I'm going to add the 4 over. So what I have now is -1 times x minus 3 times x minus 3. We FOIL out that x minus 3 squared. And when I do, I get x squared minus 6x plus 9. I distribute the -1. And then I add the 4 across. And then I get y equals -x squared plus 6x minus 5 as my standard form equation. This allows me to go ahead and solve the next two pieces for 38. One is asking what are the solutions to the function. So this is actually going to be the factors or the zeros. So this is where my graph crosses the x-axis. I don't need to do it from here because my graph actually shows me where it's crossing or touching the x-axis at. And those are the x values of my x-intercepts or solutions. And then my y-intercept is not apparent on this graph, but the really, really cool thing is that the y-intercept of a quadratic is the constant on the end of the equation in standard form. So my y-intercept here would be -5 because that was the number on the end of my equation. This feeds directly into 39, I'm not going to go over 39 with you. You can see all of the work in there. It kind of works the exact same way, except we don't have to graph. Okay? So the next problem we're going to look at is 40. On number 40, we're just combining or simplifying. So I have negative 4i minus the quantity 2 plus 6i minus 4i. In order to combine these, I like to write them out without the parentheses, which means if there's a negative in front of any of my parentheses, I have to distribute it in. So I end up with negative 4i minus 2 minus 6i minus 4i. I like to put like terms together. So anything that has an I can put together. Anything that doesn't have an I can put together with anything else that doesn't have an I. The really cool thing is I just have one term here without an I, so it's going to be by itself. Then I simply add together all my terms that have an I in them. So negative 4 plus negative 6 is negative 10. Minus 4 is negative 14i. So my answer is negative 2 minus 14i. So that was 40. Let's go ahead and look at 41. 41 is another beautiful complex number. So I have negative 6 minus 2i squared. So whenever I'm squaring something like this, it simply means I'm multiplying that factor by its times itself, which means I'm going to have to FOIL. So I'm going to color code this so you can see what's happening. Negative 6 and negative 6 is a positive 36. Negative 6 and negative 2i is a positive 12i. Negative 2i and negative 6 is a positive 12i. And then negative 6 and, or sorry, just kidding. Negative 2i and negative 2i is positive 4i squared. So from here, I like to put like terms together, which here is going to be 12i and 12i. So I end up with 36 plus 24i plus 4i squared. Whenever we're talking about a complex number, we talk about it having a real term and an I term, but never an I squared term, because I can actually simplify I squared. I squared is equal to negative 1. So anytime I end up with an I squared in an equation, at the end, I need to replace that I squared with negative 1 and then re-simplify. So this plus 4i squared actually becomes plus 4 times negative 1, which becomes a minus 4, which I can then combine with that first number on the front. So 36 minus 4 is 32, plus 24i is my final answer. We're down to our last 4. Woohoo! Okay. So 42 is a good one for rationalizing the denominator. So I have 4 times the square root of 56 over the square root of 21. When we're rationalizing the denominator, I'm just finding a way to simplify it that keeps a square root out of my denominator or gets rid of it if it's already there. In order to rationalize this denominator, I need to multiply the numerator and denominator by that radical that I'm trying to get rid of. So when we multiply fractions, we multiply straight across. So this becomes 4 times. When I multiply two radicals, I just go ahead and multiply the numbers underneath them. So 56 times 21 is actually 1176. So I have 4 times the square root of 1176 over a square root times a square root cancels, and I'm just left with the number underneath, which is 21. Of course, from here, I get to simplify it because that's what we do. So I'm going to go ahead and do a factor tree for 1176. So the first thing I notice is that this is even, so I divided 2 out. So when I divide 2 out, I'm left with 588. Clearly, I can break that one down farther. When I do, I get 2 and 294. Break it down again. I get 3 and 98. Break it down again. I get 2 and 49. I can actually stop here because 2, 2, 3, and 2 are prime, and 49 is a perfect square, which means I don't have to break that down further because I already know what's going to happen. Okay? So then I go ahead and write this out. So I have 2 times 2 times 2 times 3 times 49. I put like terms together, so 2 and 2 makes 4 times 2 times 3 times 49. Nothing else is identical, so I go ahead and square root each of these and then simplify. Square root of 4 is 2. Square root of 2 stays the square root of 2. Square root of 3 stays the square root of 3. Square root of 49 is 7. I put my whole numbers together. 2 and 7 becomes 14. And then I go ahead and put my radicals together. 2 times 3 is 6. So I end up with 14 times the square root of 6. Of course, I'm not done. So I have to now take this 14 root 6 and replace the square root of 1,176 with it. So when I do, I get 4 times 14 times the square root of 1,176 all over 21. I can multiply the 4 and the 14 together. And when I do, I get 56 times the, square root of 6. 56 times the square root of 6 over 21. Then I see if I can divide anything out of 56 and 21. Turns out I can take 7 out. And when I do, I'm left with 8 root 6 over 3. Because 56 divided by 7 is 8. 21 divided by 7 is 3. 43 we're not going to do, but I can tell you that it kind of works the same way. I would like to get an I out of my denominator. Since there's nothing being added or subtracted to that I term, I can just multiply I into the numerator and the denominator, and I can simplify using I squared in there, okay? Which means we can go directly to 44. 44 is 8i over 3 plus 6i. This kind of works the same way as the previous problem, so 43 and 42 actually. My goal is to get I out of the denominator and get it down just to one number if possible. So in order to do that, I need to multiply something into the numerator and the denominator. This one is different though because I have a number plus my I term. So in order to actually get rid of it, I need to multiply by what we call the conjugate. So this means I need to multiply the top and bottom by 3 minus 6i. So the conjugate of a number just changes the sign on the inside. So it went from 3 plus 6i to 3 minus 6i. Once I do that, I just multiply straight across. 8i times 3 is 24i. 8i times negative 6i is negative 48i squared. Over, I'm going to go ahead and FOIL this denominator. 3 times 3 is 9. 3 times negative 6i is negative 18i. 3 times 6i is 18i. And then negative 6i and 6i is negative 36i squared. I need to go ahead and simplify this. The i's cancel in the bottom. I know negative 36i squared becomes negative 36 times negative 1, which becomes a positive 36. I can then add this to the 9 that's already there, which means I get a 45 in my denominator. And then I can go ahead and simplify in my numerator as well. This negative 48i squared becomes negative 48 times a negative 1, because that's what I squared equals. And a negative times a negative becomes positive. So that becomes a positive 48 plus 24i. The last step once we get here is to ask ourselves, okay, can we take anything out of 48, 24, and 45? The answer is yes. I can take a 3 out of each of those, and when I do, I'm left with 16 plus 8i over 15. And then we are done. So the last problem, number 45, is just another quadratic formula one, except I'm going to end up with a negative under my square root, which means to make it positive so I can reduce it, I have to put an I out front, which cancels out the negative inside, and then I reduce it just like normal. So I'm going to let you work through that one on your own. Of course, if you have any questions, please feel free to come and talk to me in the morning before your final.